Hi guys, Mrs. H here. Today we're going to be looking at chemical and physical properties. So by the end of this lecture, you'll be able to compare chemical and physical properties, be able to identify the differences between them, as well as some definitions. So remember, physical properties include color, volume, state, mass, density, temperature, and conductivity. So the physical properties are the properties that describe the substance. So when we look at physical and chemical changes, a physical change is only altering physical properties, where chemical changes are actually looking at the chemical makeup. And so let's look at some of these physical changes. So physical changes include temperature, state, and shape. And the substances aren't broken down and they remain intact. And so the only thing that's happening is their appearance is changing, but the substance itself stays the same. So when we have a change in state, we still have the material in front of us. On a molecular level, the only thing that's happening is those molecules are either moving faster or slowing down. The actual composition stays the same. If I cut or grind or mix or blend, again, all I'm doing is in one of those making the pieces smaller. But what's inside, again, on that microscopic level, still remains intact and still remains the same. I'm just making them smaller and smaller and smaller and smaller. And depending on the process we're using, just depends on how small we're getting it. So obviously, the blender is allowing it to cut it up really, really small, as opposed to just ripping it with a piece of paper. Physical changes can be separated if they're a mixture. So if I have, coffee or Kool-Aid, I can separate those substances into their individual component without changing their chemical makeup or their chemical composition. So remember, when I'm thinking about a physical change, the substances remain the same before, after, and during the process. So if a chemical change occurs before, after, and during, the chemical composition hasn't been altered or has not been modified. So evaporation or filtration or chromatography, those are all ways to separate mixtures so that I can isolate the components of the mixture. So examples of physical changes. So when I'm making a smoothie or shake, again, all I'm doing is making those fruits and vegetables really, really teeny and mixing them in with milk. All of those things are still the fruit that you started with, the milk that you started with. And again, over time, if you let your coffee sit or let your smoothie sit, you can actually see the components separate naturally. If I cut wood or chop vegetables, again, I'm not changing anything on a molecular level. I have no new substance. I'm just making the substances smaller. That's the only thing that's happening. Boiling water. So remember, when I boil water, that's changing the state. So the water molecules are only moving faster and at a faster speed, and they're actually spreading out farther apart from each other or rolling or sliding. And so I still have water. I'm just changing the state of water. This is reversible. Obviously, I can turn off the water and the temperatures will cool down and I can throw it in a freezer and it'll become a solid again. So again, the water stays intact on that microscopic level. So melting ice cream, again, same thing. We're just changing the state. We're going from a solid to a liquid. I can again put it back in the freezer and it's going to become a solid again. So the molecular makeup is still the same. cracking an egg. So when I crack that egg, I'm putting the egg into smaller pieces. Um, I'm separating the inside from the shell. So again, all that's happening is a physical change, not a chemical change, because the molecular makeup has stayed the same. So characteristics of physical properties: no chemical bonds are broken, no new substance is formed. Examples are change in temperature, change in state, or ripping or tearing or changing the size. And these can be reversible. Now, sometimes they can't be reversible, but typically speaking, we see them as reversible. So now let's look at chemical changes. So, oops, sorry guys. So chemical changes result on a change on the microscopic level. So we get a new substance. So we're changing the water into oxygen or hydrogen, for example. So we're getting something different. And how that happens is we're changing and we're altering the chemical bonds that make up that compound. So an example would be photosynthesis. So the plants take in oxygen and take in the oxygen and the water, and they rearrange the molecules into sugar, into a new compound. So what I start with is different from what I end up with. So oxygen is much different than the carbon that we start with. So examples of chemical changes. So when we're cooking and baking, any cooking and baking, when you're putting it into an oven or you're putting it in a pan, we are changing the chemical composition. Now, the only time that this wouldn't be a chemical change is if you're boiling water in the pan. So when we, fry the egg, we can actually see the egg change on it. We can see the microscopic changes on a macroscopic level because it looks different. That egg white looks different after you cook it. Same thing with baking. That mixture in the bowl and you put it into the pan, it looks much different because it's a new substance. We have broken the bonds. Rotting is another example, or something going spoiled. It's altering the chemical composition. That mold that's on it is actually breaking down the sugars in the breads and in the fruits to something different. And again, we have a new substance being formed because those bonds are being broken. So on a macroscopic level, there are changes occurring. And again, this is irreversible. Rust. Rust is another example of a chemical change. So when we have metal being affected by the water and the air, and it's turning that brown color, that rust color, that metal becomes very brittle, it becomes tarnished, it looks different. Because what's forming? Actually, what's called iron oxide. And this is an irreversible process. We can't get the iron back. It's gone. We can't fix that. So rust is an example of a chemical change because the arrangement of the atoms have changed. Same thing with burning a candle. So we have wax as the fuel, and what do we end up with? We end up with carbon dioxide and water being produced from the wax. And again, we no longer we have a new compound. We have new material. Fireworks, again, same thing. The fireworks, we have a fuel source and we have a heat, and so we have a chemical reaction. And depending on what we're starting with will depend on what color is produced. That's why we get different colors in our fireworks, because of what material we started with will produce a different chemical compound after the firework goes off. And again, these are irreversible. So things to remember with a chemical change: we have a new substance. There's something different from what we started with. These are irreversible. Now, that's not, again, entirely true. There are some chemical equations that are, or reactions that are changeable. We see a change in color, change in temperature or a change in smell would indicate but a chemical change, but not in and of itself of temperature. If we see light or sound, again, a sign of a chemical reaction. But on that microscopic level, what we start with, all of that stuff rearranges to form something new. So go ahead and take a minute and think about what these three things are. Are these a chemical change, a physical, or a physical change? If you have any questions about the differences between chemical and physical changes, make sure you're reaching out to me. Otherwise, bye guys. Have a good day.